Welcome to the how-to for electron configuration and orbital diagrams. So when we talk about electron configurations of the atom, we're really just looking at where the electrons exist and kind of writing it out. Whether we show it in little orbital diagrams, little boxes, or we just write out where those electrons exist. One of the things we have to remember is the atomic number tells us the number of electrons, right? The atomic number is the number of protons, which in a neutral atom is equal to the number of electrons. So if we were to look at something like lithium, when we think of lithium, we could look at, and so when we go back and we think about the atomic number for lithium is 3, that really tells us our electrons are going to be in the lowest energy orbitals first. And anytime we fill the orbitals, hopefully you remember that the 1s is the lowest in energy, then we go 2s, then we go 2p, we go 3s, we go 3p, we go 4s, then we go to 3d, and so forth. Okay, and so if you go back and review the energy levels for these different orbitals, you'll see this. And so with lithium, we only have 3 electrons. We know each orbital can hold a maximum of 2 electrons, which means that we just start out writing lithium as 1s with 2 electrons, and then the 2s, we have 1 electron left over, and so that's all that's in there. We can also depict this as what we call orbital diagrams. And so you see an orbital diagram down here, where basically we show the exact same thing. We just show either the 1s orbital or as either a box, kind of drawn here, right? Or you could just draw it as a line. And then you can put those electrons in. Each orbital holds a maximum of 2 electrons, and they have to have opposite spin. That's why you see that one kind of pointed as this half arrow up, the other is pointed as a half arrow down. And so each half arrow represents the electrons. And so we could draw this here as well. Doesn't matter if you put the one going down first or second on the periodic. So Hund's rule just talks about degenerate orbitals, which means that orbitals with the same energy. A good example of a degenerate orbital are the 2p, right? There is the 2px, there's the 2py, and there's a 2pz, right? And so there's 3 of them, but they're all the same. They're just oriented slightly differently. So they all have the same amount of energy. So when electrons go into these orbital diagrams, we add them according to Hund's rule, which says that the lowest energy is going to be attained when the number of electrons having the same spin is maximized. Meaning that when we look at an example of nitrogen, nitrogen has an atomic number of 7, which tells us it has 7 electrons. And so if we were going to write out the electron configuration, we get 1s2, 2s2, 2p3. That's a total of 7 electrons. But we could also depict this in the orbital diagram. So we know that the 1s has 2 electrons in it, 1 up, 1 down. The 2s is also telling us that we have 2 electrons in it, 1 up, 1 down. The 2p says that we have 3 electrons, and we know the 2p subshell can hold a total of 6 electrons, where each orbital has 2 electrons. So instead of putting 1 up and 1 down in the first box, we actually show 1 in the first box, 1 in the second box, and 1 in the third box. We first add so that they all have the same spin. This results in having the lowest energy, and this is according to Hund's rule. Table, and we see that where we find lithium is right here, right? And so it has an atomic number of 3. Another important thing to note here is that we can look at the periodic table of elements, and it tells us a lot about the electron configuration in the orbital diagram. Because essentially what we have is, if we just start on the periodic table and work our ways across, so let's start here at hydrogen. Hydrogen has 1 electron, and that 1 electron is in the 1s subshell. Well, helium has 2, and it's in the 1s1 and the 1s2. If we move down, we're now in period 2. And in period 2, this becomes the 2s1, 2s2. Move over, this is 2p1, 2p2, 2p3, 2p4, 2p5, and 2p6. And then we can continue doing this across the periodic table. So really, it kind of shows that we have these different sections on the periodic table. We have the s orbitals, we have the p orbitals, we have the d orbitals, and then we have the f way down here. The key being that if you just pick whatever element you're looking for, if we use lithium again, and we said, okay, well, what is the electron configuration for lithium? Well, if we just start counting these off, well, this is the 1s, and that would be the first electron. But we also have this helium over here, which would be 1s2, right? That's the first 2 electrons. And then we move down the periodic table. We're now on period 2, but we hit lithium, which tells us that we have 2s and there's just one electron in there. If instead we were talking about beryllium, we would have 1s2, 2s2, because now we've used this one, and now we land here. We could continue to do this. So for nitrogen, we would end up with 1s2, 2s2, and then we have the 2p1, 2p2, 2p3, right? This is the p block. We're in the second period, so it tells us that. The one thing to keep in mind is that when we get to the D block, so down here, where we're talking about the D block, in this case, whenever you hit this first box, we're in the n equals 4 electron shell. But when you're talking about the D block, you have to remember an important rule, that the D's are n minus 1. So in fact, this is no longer the 4, this is the 4s1, 4s2, but when we get to the D block, it's actually reduced by 1. So now this is the 3. And so we would call this the 3D block. This one would be the 4D block. This would be the 5D block, and this would be the 6D block. For the F's, it's actually n minus 2. So for F, it is n minus 2, which now means that here we actually have the 4F, and here we have the 5F. Right before lithium. So when we go back and we look at lithium, lithium is here, right? If we just back up 1, we're at helium. So we can show that everything up until helium, and then 2s1. The last thing I want to talk about is condensed electron configuration. We're actually condense down our electron configuration because some of these could get really, really long. And so to make it a lot shorter, we actually just look at what we call the core electrons and the valence electrons. Core electrons are the inner shell electrons of an atom. So if we think of something like lithium, lithium has 3 protons in its nucleus. We have the n equals 1 shell, and we have an n equals 2 shell. The core electrons are the innermost electrons, and so we know there are 2 electrons in this innermost shell. Why do we know that? Well, we said that the lithium is 1s2, 2s1. That is the electron configuration. It tells us that 2 electrons are in the n equals 1 electron shell, and they're both in the s orbital. In the 2s, there's 1 electron left over, so we could draw that here. So our core electrons are everything in the inner shells. The outermost shell, the one with the highest principal quantum number, here is 2, is actually going to be our valence electrons. These are the outer shell electrons. They're going to be the ones that are going to be gained or lost during a chemical reaction. What happens is we can abbreviate the core electrons using the last known valence electron. The last noble gas electron. And so in that case, helium was the noble gas. So this just says it has the same electron configuration up to helium, but then it also has this 2s1. You can see other examples down below. That concludes the how-to for electron configuration.